And it gives me very great pleasure to introduce our next speaker, who is John Hinch. John Hinch is Emeritus Professor of Fluid Mechanics at the University of Cambridge. His PhD was supervised by George Batchelor and examined by one Anthony Pearson in 1972. So John's research interests include suspensions of particles and other mobile particulate systems, the flow of non-Newtonian fluids, and applications of mathematics to industrial problems. Actually, I think John is very well known to very many people on this call. So today he's going to speak about the much neglected second normal stress difference, which I think is a very unique title in its own right. So John, I'll pass over to you. Thank you very much.
Thank you. I'll try and share my screen. Okay. So non-Newtonian fluids are very much one of Anthony's interests, and they've not been mentioned much today. And looking at the audience, not so many of the audience are rheologists, so they won't, not many of them will know about what is a much forgotten corner of non-Newtonian fluid mechanics, which I'm going to try and talk about. So first I better define normal stress differences, the first and the second, before I get on to the neglected second. So in a simple shear, that's flow in the x direction, where the velocity increases linearly in the y direction. This is a very common flow of a laminar flow of layers of fluid sliding over one another. The shear the stress tensor takes the form I've displayed, with the off-diagonal terms being the tangential viscous stresses that dissipate all the energy. And the blue diagonal terms are called normal stresses because they don't do any work. In a normal fluid like water or air, the diagonal terms are all equal and equal to minus the pressure. And it's in the elastic liquids that the diagonal terms are not equal, and one is interested in the differences which reflects the elasticity of the fluid. So the difference between the flow direction x and the velocity gradient direction y is called n1, and the difference between the y velocity gradient direction and the z vorticity direction is called n2. So be very much talking about the vorticity direction z in this simple flow in the x direction with a velocity gradient in the y direction. Now, when I was a research student and learning about rheology from Anthony, the non-Newtonian fluids were polymers, polymer melts, polymer solutions. And for them, there is an N1, which is big. That corresponds to a stress in the x, the flow direction. It's a tension in the streamlines. And there's not much of an N2. In fact, it's so difficult to measure, it was even suggested that it doesn't exist. Why bother about it? So that's where the neglect started. So let's just quickly review what N1 does for you. There's a number of non-Newtonian phenomena which are driven by this tension in the streamlines. The most dramatic one is rod climbing in that little picture, famous picture. There's a vertical rod which is spinning around its axis, and the liquid isn't thrown outwards as by inertia, but does precisely the opposite. And it is attracted to the rod. Why? Well, the streamlines are circles around the rod, and there is tension in those streamlines. And as you go towards the rod, the shear rate's getting higher and the tension is getting higher, and it squeezes through a hoop stress effect the fluid inwards, and it has to go somewhere. It goes up, and it goes up until the weight of the fluid above you is sufficient to balance the inward squeezing of the hoop stresses. And you can all go away and just try this out. Just try beating some egg whites. They'll do this for you. So there's lots of other things that can be explained. I just pick up on the third one, migration of particles to the center of a pipe flow or channel flow, because Simon mentioned this earlier. So in a channel flow, the velocity, the shear rate is 0 on the centreline and is maximum at the walls. Those flow lines down the channel, down the pipe, are in tension. And if we have particles in that flow, then the streamlines that go around the particles on the wall side will be in higher tension than those on the centerline side. And so those higher tensions on the wall side will just nudge the particles and they'll all migrate to the center of the pipe, typically quite quickly. So it's useful to understand where did N1, the first normal stress difference, come from. So for polymers and any other complex fluid with a microstructure made of fibers, you start on the left-hand side with a fiber, you put it in a shear flow, it becomes stretched and aligned with the flow in the right-hand side. So it's stretched and aligned with the flow. This is tension in the streamlines. And that's all there is there. There is no activity in the vorticity direction. So there is no second normal stress differences for fibers, for polymers. And that's why it has, the N2 has become much neglected. If you want to have some N2, you need a microstructure which is a bit bigger than fibers, a bit thicker than fibers. For example, droplets. You have liquid droplets in an emulsion, then they have a thickness, and the thickness can be compressed. In that simple shear, the principal stretches are, can you see my pointer? There's a line, diagonal line through where they're being stretched out by the stretching, and at 90 degrees, there is a compression. And then if we were to just spin that drop round with the vorticity, we would have some pressure as it's trying to push out in the y direction. So if we look at N2, we have pressure, that's negative stress, pushing upwards and downwards, and we don't have anything happening in the vorticity direction, Z, so we have a negative second normal stress difference. And rather than saying it's a negative Y, that is equivalent in that difference to being a positive Z, and that would be a tension in the vortex lines. So this entire talk is going to be about tension in the vortex lines. So there are a few rheologists present, I notice. So this transparency is entirely for the rheologists. Everyone else can ignore this for a moment. So these thick microstructures, it turns out, put in a pure straining motion, they don't strain with the imposed flow totally, not 100%, 50%, say. I actually know what it is for liquid drops, as it depends on the viscosity of the drop compared with the velocity of the external suspending fluid. So the microstructure deforms with not the velocity gradient, but the antisymmetric part of the velocity gradient, which is the vorticity, because there's solid body rotation and it will rotate with solid body rotation. But the straining motion is reduced to 50% of the strain rate, the symmetric part of the velocity gradient. So if you put that in your favorite time derivative, what you find is you automatically get a second normal stress difference proportional to that inefficiency, and you get a shear thinning effect as well. Okay. Oops, no. That's one origin of the second normal stress difference. And there is another one which I found out about only a few years ago, and that is in non-Brownian suspensions, bigger particles that don't suffer from Brownian motion, they suffer for particle-particle impacts. So here I've got in a suspension, two particles moving along in their shear flow, about to pass one another. They impact, and that leads to a pressure resisting in the direction of the flow, that's sigma xx. When the suspensions are concentrated, there are other particles than the two I've just shown here. There is an awful lot of particles above and an awful lot below them. And in order for these two particles to move round one another in that shear flow, they have to bash an awful lot above them and a lot below. And they pick up a lot of pressure impact in the y direction. In fact, for those who've looked at granular flows, there are force chains very much aligned at 45 degrees to the flow, which means that the y stress and the xx stress, these two pressures in the x direction and the y direction, are pretty equal, and N1 has suddenly gone to 0. On the other hand, there's no real difficulty of going sideways in the z direction, the vorticity direction, so there's not much of a pressure in the z direction. And so N2, which is pressure in the y, that's a negative stress, and nothing in the z, ends up again being negative. And this was nicely measured by Elizabeth Guazelli's group. Okay. So this tension in the vortex lines can lead to a number of phenomena. And I'm going to talk about some well-established ones and some lesser known phenomena, which are entirely due to this second normal stress difference. So it was really Roger Tanner who found out how you might be able to separate off N2 from N1 and measure it. And it's a clever device. It's a V-shaped channel, which is inclined to the vertical. So the liquid in the V-shaped channel flows downhill. And in that flow downhill, in the center of the channel, it flows faster. And in lubrication theory, as it's been mentioned, it flows proportional to the local depth squared. So that means that the shear rate will be proportional to the local depth to the power 1. So it means that along the center of that V-shaped channel, there's a higher shear rate than there is at the edges. That's virtually obvious anyway. And therefore, there is a greater tension in the vortex lines, that's in the sort of horizontal lines there across the channel. There's a greater tension in the center than there is at the edges, and that pulls the fluid into the center, and it makes the free surface bow up. So that's Roger Tanner's device for measuring N2. And I think this mechanism of Roger's may be appropriate to granular chute flow and the formation of longitudinal vortices in flow of granular material down a chute. Forterre and Poulequin have an alternative explanation, and I speculate this mechanism might be simpler. Rod climbing. Now, that rod climbing, there's an analysis by Dan Joseph that gives an expression for how the free surface is deformed if we ignore surface tension effects. And it depends not on just the N1 that I gave an explanation for, but it depends also on N2. But of course, in the polymeric world, N2 wasn't there, so no one noticed that. Right, so in polymers, N1's positive, N2's negligible, so the free surface goes up, the liquid climbs the rotating rod. However, in these non-Brownian suspensions, N1 is pretty near to 0, N2 is negative, and therefore the free surface near to the rod goes down. So it's not rod climbing, it's negative rod climbing or rod dipping. And this is caused by tension, not in the N1 gives you tension in the streamlines around the rod. this N2 gives you tension in the vertical vortex lines. Some work by Elizabeth Gozeli's group. Now, here's another phenomena that Roger Tanner was came up with the first explanation. Well, nearly did. Peter Olmsted revisited this a few years ago, and it was Suzanne Fielding who gave the first sensible linear stability analysis and a big numerical nonlinear analysis. So what is happening? To measure viscosities, you often have a plate, a circular plate, and you put a blob of liquid on it, then you put another circular plate on top, and you rotate the top circular plate and measure the torque to measure the viscosity of the fluid. And sometimes, depending on the viscoelastic nature of the liquid won't stay between the two plates, it just flies out. And it does it not through inertia, but through non-Newtonian stress effects. So this is looking at that phenomena of the fluid flying out from between the two rotating discs. Now the discs I've got here, I'm looking just at the edge with the liquid inside and air outside, and the disc extends way out to the right. The center of the disc is miles away. And we've got a blue disc at the top, and we've got a blue disc at the bottom. The blue disc, in the way we're looking at it, on the top is coming towards you, and the blue disc on the bottom is moving away from you. And then we have a shear flow between the two. And the contours of constant velocity towards or away from you in the x direction are essentially horizontal out on the right-hand side. Now we consider the interface between the liquid and the air being perturbed a bit. Instead of being a straight line between the top and bottom plates, there's a little indentation at A into the liquid. These contours of constant velocity u have to meet this interface at right angles. If they met not at right angles, then there would be a component of the velocity gradient of the gradient of velocity u towards the interface, and therefore there would be a shear stress exerted by the liquid on the right on the air on the left, but the air can't stand any tangential stresses exerted on it, so you can't have that. Therefore the contours have to come into this interface at right angles. People who have studied thermal problems with insulating boundary conditions know the same thing, that the temperature has to come in, temperature isotherms have to come in at right angles to the interface. Now this effect of coming in at right angles means that the contours have crowded around the point A, and this means there has to be therefore more change in the velocity u in the vicinity of A than normal. That means there's a higher shear rate there. This means there's a higher tension in the vortex lines at A. The vortex lines are the horizontal lines of constant, these contours of constant velocity, and therefore we're going to pull in with this higher tension in the vortex lines at A. We're going to pull A in to the right, and therefore you've got yourself a little instability. How am I doing for time? Fine. Oh. So here's another phenomena that I've done some research on, although not published, is some experiments in Laboratoire FAST in Paris. Is a paper in JFM. And the most interesting part of their study isn't in the paper in JFM that I've referenced there. It's only available in the thesis of Francois Boulogne. And I've got a video, but I can't play videos by Zoom very well. So in the thesis, it explains that for non-Newtonian fluids, which are on a vertical fibre, so there's centrally there is a fibre which is vertical, and it has a coating of liquid, blue liquid around it. And when the blue liquid is non-Newtonian of a certain sort, it's found that the coating doesn't remain of a uniform thickness all the way around the fibre, but develops a lopsidedness. It develops it's thicker on one side than the other. In fact, it goes to totally de-wetting. So all the liquid ends up on one side and leaves a dry side on the other. The mechanism is this N2, that as the liquid is falling down the blue liquid is falling down the stationary black fibre, we have shear, and we have a higher shear rate on the left-hand side where the coating is thicker, where we have a higher shear rate on the left-hand side, we have a higher tension in the vortex lines. Vorticity in this case is circular lines around the fibre. So we have a higher tension on the left-hand side, and that will just pull the liquid from the right-hand side round to the left-hand side. And so it will wet. Now we can study this with a little mathematics if we've got a few moments, which we think we have. You can set up for a thin coating, so lubrication equations. I've ignored the variations in the direction of gravity downwards and just worried about how the coating thickness H varies in time with theta around the fibre. So we have a normal H cubed response for the flux depending on the pressure gradient. There's a pressure gradient in the theta direction, and the pressure gradient has two contributions. There's surface tension, the two terms H, theta, theta, and H, and the non-Newtonian tension in the vortex lines is the purple B term, which is a non-dimensional version of the second normal stress difference, N2, and it's the psi, capital psi 2 is the coefficient by which N2 varies quadratically in the shear rate that the rheologists will know all about. So I've just solved this numerically. The coating starts fairly constant at H equals 1 for all theta, nearly. And you can see that as time increases, you have to take bigger and bigger leaps in time to see anything happening. You can see that the shape is developing towards, there's a blue dotted line you can see on the left-hand side at 3.35, and the blue dotted line goes all the way down to H equals 0 at theta equals 2. That's the steady state you can predict. And you can see it's evolving towards the steady state. There is a very interesting, on the right-hand side, a little dimple, which is proving remarkably difficult to drain out in order to complete the de-wetting. There's a very slow feed from the right-hand side little dimple into the main lobe on the left-hand side. And one can go away and study that. Oops. Oh. Sorry, we were there. And there's a draining which goes at t to the minus a quarter. So you can see I'm plotting the thickness at the right-hand side going down to 0 as t to the minus a quarter goes to 0, as t goes to infinity. I even know the coefficient. And just to relate it to another talk today, this is something that's nearly in Paul Hammond's thesis of a few years ago. Right. So I've given some examples where what was neglected N2 should not be neglected because it's responsible for non-Newtonian phenomena, right, it shouldn't be neglected. And there's a speculation, that second one, which I've put out just to see if I'm correct. And so that leads me back to Anthony. This last problem of the de-wetting, it has 4 interesting features. It has an application to the real world. The thesis was sponsored by L'Oreal. It has non-Newtonian fluid mechanics. It has surface tension. Sorry, it doesn't have Marangoni effect, but it has surface tension. And it has an asymptotic analysis. All these 4 features are very much aspects of Anthony's pioneering works in the 1950s. and it's inspiring. He inspired us then, and he's inspiring us today. So happy birthday, Anthony.
Thank you very much, John. I thought that was excellent. And may I say that we can now call it the less neglected second normal stress difference.
Thank you.
Very good, thank you.